Okay, so good evening, everyone. How's the week going? We're closer to the weekend, though, right? No response. Okay. Uh, so let's see. So when is the submission deadline for assignment one? Next week? Assignment two. Yeah. Um, yes, some people are already onto some interesting tasks. So people have not started, definitely started because it requires a little bit of thinking, and you want to use PyTorch, so you want to know how to use PyTorch, especially for the CIFAR example, as well as even the movie recommendation part. You'll understand embeddings in a different context than the ones that we saw: image embeddings and text embedding. Word embeddings. We'll see something else in the assignment. Okay. Um, So today, what I'll do is actually in the syllabus it said BERT for the previous lecture, but BERT is actually supposed to be after is part of this lecture. Okay, BERT is some particular architecture for language modeling. So today we'll see some language models. If you remember last week we were talking about NLP, and we were looking at some simple language models like Marco chain, Marco n-gram models. Basically, that's what they're called, where you kind of keep empirical statistics of, oh, if the previous two words to this, what is the most likely next word that can happen, what is the next most likely word that can happen. You'll compute those empirical statistics, and those would be the uh, you know uh, that could kind of constitute your model. And if you look at, for example, on your phones, typically they will probably implement uh, that type of a model, because although it has too many parameters, it's kind of a very simple idea. Okay, so today we'll look at, so the theme is basically to look at, and if you and last time's language model was an example of this situation where the problem, these prediction tasks, the supervised learning tasks will have some sequential dependencies. So a sentence being translated to another sentence in some other language, for example, has sequential dependency. You can't just jumble the words, and it may not even have the same meaning, or it may not even have any meaning. Okay, so when prediction tasks involve sequential dependencies between parts of the input and parts of the output, how do you kind of model that? That's the core goal for today. And there are two kind of ways to do it. One is based on the idea of a recurrent neural network. Okay, a specific version of a recurrent neural network is called an LSTM. So that's the third goal. So we want to understand what is recurrent neural network solving, which was not there before. As I said, it's about sequential aspects of the input part and non-sequential aspect of the output part. And then we look at a specific instance of an RNN, which is called an LSTM. And we look at a few applications and throughout we'll kind of understand some applications of sequential models. And then towards the end, we'll talk about some newer architectures, especially in language processing, which are uh, popularly called transformer networks. Uh, I don't know if you've heard of OpenAI not releasing a particular large language model because people may abuse it. Did you guys ever hear it? It was there a few months ago where OpenAI is a non-profit or for-profit now firm. They trained a bunch of really well-performing language models, basically deep learning models, and then they kind of withheld releasing that model uh, to the public, saying that there could be abuse and so on. Basically, what can you do with the language model? You can do many different things. You can use that language model for a basket of different NLP tasks. Okay, for example, you can use it to generate synthetic text. For example, maybe an automatic way of writing a news article. You can start with some lead words, and then the language model itself will fill in a few words. Of course, it will not know the news content, but things like that. Okay, and it can also be used for regular NLP tasks like um, NER or any of these regular traditional tasks. Okay. Um, anyway, so that's the goal. And actually, before that, I wanted to kind of quickly go over. So did anybody look at Git workflows? I mean, how to work with Git? How many of you are already familiar with Git workflow? One, two, three, four. What about the remaining? You've heard of GitHub and created an account with GitHub, for example? You have. Okay. So you have an account with GitHub, but you already know how to work with cloning a repo, making changes, making a commit, and all that.
No, I don't.
No. Okay, that's fine. Goal zero is to just kind of revisit some workflow because it kind of makes life a bit easier. So let's see. So there are several links here. We can follow, I guess, the second one. So what's the core idea of Git? Git is just a version control, I guess, software. There are many such version control softwares. Actually, Git is a specific version of a distributed version control. Uh, and what is version control? It's basically timestamping your progress. Okay, in your code, you write new functions. You want to kind of snapshot them, and so the pictorially. Um, Pictorially, you can represent Git as like some sort of a tree, okay, where each node corresponds to the snapshot. So like you would, in the old days, you would do a manual thing like version 1, version 2, version 3, maybe subfolders and so on, right? So each node kind of represents a snapshot of the current code base, maybe file name 1, file name 2, file name 3, and then maybe you would make some changes. You can snapshot it, that would be this, and then maybe more changes, snapshot it, and so on, okay. And there are some other things that you can do. For example, you can branch. Okay, you can branch and create some other. Branch just means making a. So it's like a tree. Okay, this is just a backbone of Git. Just to understand what's going on, you can start from the same starting point, like the snapshot. Make some editings, but maybe you're not happy with this edits. Maybe you make a different snapshot. Okay, that's a branch. You can make a different edits and commit it as in create a snapshot here. So these two snapshots started from the same thing, but have different file edits. Okay, for example, maybe there are three files in this whole working directory that are being version controlled, and maybe from this to this you edited file one, from this to this you edited file two. Okay, so you can do that, and then you can actually merge it back. Okay, so you can also do merge operation. So if in this version and this version the only difference is file one was edited and file two was edited, then when you say merge the branch, then Git takes care of like changing file two only in this case. Okay, so that's like a very basic kind of pictorial idea. So think of each node as like a version 0, version 1, version 2 of your software, and it's very easy to kind of revert back, right? So maybe you made a bunch of changes, but then realize this is all kind of useless or incorrect. Then you kind of can revert back to any of these snapshots, right? Just like you know, or what you do manually. Yeah. So actually, let's try to do that here. So as you know, in Jupyter, you can actually open the terminal. Right, and so I'm just looking at the repo for our own course. Okay. Slash. Okay, so this is the current repo. I mean, this is the repo for both. This is basically the repo where we have all the notebooks. Okay, so you can clone this and just open these notebooks, for example. So, and maybe I kind of showed this to you before. Let's go back. So, how would you clone a repo from GitHub, right? So you'll just go here, get this link, right? Copy that, and I don't know if I already have it. Doesn't matter. Git clone. Um, and that's it. So you'll see that it's pretty much the same URL with a dot git here. and that's it. So you can press enter and it'll clone. So it's just a copy. Now the tree that we saw in the I was showing you 2 minutes ago. That's the tree that was there on the GitHub web server, and now we just copied the tree onto our server. So if you look at git log sorry cd into that directory, so f19, and if you look at this is a log. Okay, this is a tree where there were no branches. So this is the top of the tree where I made some commit um, today, 10 minutes ago, I guess, 10 minutes before the class started. And then here are the commits I've been making. Okay, it's basically, in my case, I'm the only one working with that repo. So it's just basically this. I'm not branching ever, and I'm not doing anything more. Okay. Um, but if you wanted to look at commits or check out and so on, you can do that. So let me. Okay, now let me just. So to create a Git repo, so you don't need GitHub to do all this. Okay, so you can just do Git init. Git is generally uh, um, gonna be present in your system. Otherwise, you can install it. Okay, but in these servers, it's already there. Otherwise, you'll have to install it through appropriate commands, and then. Okay, so you see that there's in this directory, test directory, there's only one file, file.txt, file1.txt, and I initialize the Git repo, so I can now git add this file. Okay, so this will add. So what is this process? This process I'm trying to create that node. Okay, so I added this file because it was not there. It's a new file. If there was already a file which is modified, it will show that it's modified. Okay, and then git commit minus, I guess, minus m. So I can with the each node that I showed you in the previous picture, I can add a message that, oh, what was this commit about? Okay, what is the snapshot about? Okay, okay. So okay, it tells me it's not able to detect uh, you know two settings that it needs to make that commit. So let's do that. So let me actually just copy this. It doesn't matter for now. Okay, so now if I run git minus m something, you just saw that I'm on. So the default branch is called master, and I changed one file and whatever something file1.txt. Okay, so see the log shows that your name, your example, the commit message was this, and then I can now. Okay, let's say I did this. Okay, now if I do get status, it says that this file one was got modified. So I created that first initial node, and now I'm editing this file. You can think of this adding my new Python scripts, my new functions or whatever, new experiments, and then I can again do the same thing. Again now git add of this thing. Um, and then okay, so basically says what changed in that file. For example, if there was one insertion happening. So there were two commits now. There was a previous commit, and now I changed something. I added my name into one of the files, and I committed it again. Okay. So if you look at the handbook, you should leave this link when you have time. It gives you a good. Git is not very difficult to learn, at least if you're a solo developer. There are some parts which are kind of important if you want to do things in a team. Okay, and some of you are already in a team when you're working on projects and you're working with Python notebooks. They have their own unique challenges because they'll have a lot of JSON strings which will kind of change from commit to commit. I mean, every time you start opening them, it may seem as if they've been modified when they're not. So there's some issues with Python notebooks, but in general, for a code base, you can, and in a team, it's good to work on a Git workflow. Okay, so yeah.
So I got a couple questions. First of all, what's the advantage of doing this when if we're working in Colab and Colab has backs up different versions and we can all work on the same code through Colab?
You can, yeah, yeah. So Collab is it's not an alternative to maybe it is an alternative to Git, but it's, I guess, closed source. I don't know what Collab is doing behind the scenes, how it's maintaining versions. So there are several softwares which do maintain versions, including Word will maintain versions. So this is just I mean, this is open source software which is the one being backed by, I guess, GitHub, which is the a social SaaS company which kind of pretty much runs this online. There are many other alternatives, but you can always do this on your own servers, on your own machines. There's no big difference. I mean, this is a kind of common denominator.
Okay.
Okay.
And is there a way to do those operations that we were just doing
Yeah.
without using terminal?
Yeah, there are GUIs. Yeah, there are.
Because like I don't understand it, but I have a GitHub account.
Yeah.
And it's like it comes up in my browser.
Yeah. Yeah, you can edit things here. Actually, it doesn't show here, but let's say if I mean, like for example, I can edit here. I mean, I'm not logged in, but I can edit at least text files here. But I don't think I'm not sure if GitHub is directly like well, you can't do editing. It's not an IDE, right? It's not a really good editor for editing code directly, but it works well with VS Code, for example. I don't know if you've used VS Code. It's a Microsoft product. This is also a Microsoft product, so they kind of gel well, and you can kind of not worry about writing those commands if you want.
If I wanted to clone someone's
Yeah. GitHub itself has a
directory
software.
there,
Yeah.
can you do that through the browser and put it in my own directory?
You don't have to clone. Like sometimes you don't care about the history, so you can just get the latest version by downloading a zip. Like you can download the zip, but it will not have it will not have the history. It will not have the tree. It will only have that last files, which is fine sometimes. But this is how what professional developers kind of use, like Git, not GitHub, but like a Git workflow, a good chunk. So it's good to learn.
And so if several people working on the same project at the same time,
Yeah.
they're all referencing the same.
No, they're all working on their trees, and they can kind of sync with each other. And if there are conflicts, they can be resolved. If typically if they're working on different files, there'll probably no conflicts if you merge across team members. Yeah. So they're not working on the same file, right? They're probably working on the files on their own computers, but you can sync back. Okay. So it's a distributed version control. There is no master copy, so everybody can sync to your machine, or you can sync to somebody else's machine, whatever you want. Okay, or you can sync to GitHub. Typically, that's what people do. Yeah. And GitHub itself has some other things like pull requests and issues that can be opened, which are like issues about the software. Here, these are the bugs. Let's squash them. And pull request just means somebody else making a new feature and adding it back to some open source software and so on. But these are all fine. For us, it's not very necessary. Um, where was I? Okay. So I was just saying that the basic commands are basically this, right? So cloning an existing GitHub repo. Let's say somebody wrote something in PyTorch, right? I mean, and it's already in GitHub. You can either download the folder as a zip file and unzip it and push it to the server or whatever, duplicate on the server and do something, or you can just do git clone of that repo, right? And then it's already on the server, so you can just open it on your, like that's what I did here. So here I have not test, but like f19 was something that I downloaded just now, right, by git clone. So that's over here. Oops, sorry. So I can just go in there and go to 576, and I have all the notebooks from that repo. It doesn't. And in this example, it's our class repo, but you can just download any like TensorFlow models or PyTorch models from their appropriate repos. And a lot of people re-implement many of the deep learning methods, so it's always good to do that. In fact, I think today we have. Yeah, I mean there are some. You can get some for today's material. Okay, like GitHub implementations that you can try out. Okay. So I won't spend too much time beyond this. I already spent 15-20 minutes. So what I showed is init, clone, add, and commit, and status. I did not show branching and merging, but uh, because it's not too difficult. If you're a single developer, it's not very kind of necessary. Uh, Pull and push is something I didn't show, but okay, let's see. Sorry. Um, so here you see that uh, there is a remote repo that I can sync with the current files. So current tree can be synced with a remote tree essentially, and so I can push. So if I make some changes, I can push it back to that the location indicated by this URL, okay, which is just called the remote URL, and you can have many such URLs. Okay, like if you have three other team members, they can all have their if they are publicly accessible machines, then you can have their URLs there, and you can sync up. Okay, so that's what push and pull. Pull means just pull from latest version from them, latest tree from them, and push means push your changes to them. Okay. So that's Git. Any questions about the at least the high level idea? So just think of if you get overwhelmed with Git, it's just basically there's some sort of snapshotting and a tree structure with some branches and which get branched off and merged. Okay.
So what is the difference between push and commit?
So commit is a local snapshot that you're creating, like a new circle here. So push is like um, you are trying to replicate the same tree in some in this case the GitHub server side. Okay, the GitHub server has its own tree, right? So maybe that tree doesn't have this additional node, so it will get copied over there. Any other questions? No. Okay, let's actually start today's. Where is it? I already discussed the goals. The goals is to learn sequential settings, RNN and LSTM architectures, and hopefully, if we have time, we'll talk about transformer networks. Okay. Okay. Let's. Okay. So let's start. So RNN. So at the block level, we want to understand different prediction tasks. So the first task is what we have kind of seen so far. You have a fixed size input and a fixed size output. And, regular classification task. The input size is fixed, right? It's a 100-dimensional vector, or like whatever size is the image size is the fixed size, and you want to kind of produce one of the k classes, right? Like 10 classes in CPAR 10. That's one-to-one type of a situation. And now the remaining are actually what are called sequence-to-sequence settings, where, for example, you want to go from image to a caption of that image. So it seems at least non-trivial when you first hear about it, but it's actually doable. So the input is a fixed size input, an image, and somehow you're able to create a caption for that. Okay. Of course, for all these tasks, by the way, these are all supervised learning tasks. You need to have a corpus where there are images and captions already in your training data set. Once you have that, you can train models which can at test time, given a new image, can create a sequence of create a caption, right? So that's a second example where the input size is fixed, output size is variable, and then the third one is for example, like a variable length input, like a sentence. Sentences need not be all the same length. Variable length input to a single output, right? Like sentiment classification. And then this guy is like the typical what you say machine translation, which is the kind of the key example, and kind of the important tasks, which is what people are trying to improve pretty much recently. So here basically the length input is variable and output is also variable length. Okay. So like think of converting from English to Chinese or something like that. And there are others where the only difference is that you start producing output without waiting till the end of the input. Okay, so you can think of it as like video classification where there is temporal dependency across frames, so you don't have to wait till the end of the video to say something about like maybe say something about the video, right? So those are some application categories, and core idea for any of the models that you'll see today, basically two major classes, RNNs and then transformer models. The objective is some to capture some sort of persistence, which is that the input, let's say think of a sentence, then there's information that is uh, that needs there's information across the words in that sentence, as in the parts of the sentence, they're not like interchangeable. There is a temporal order and information that we want to use. Okay, so feedforward networks and neural networks kind of, they do have, of course, a fixed input structure, but they don't explicitly model this persistence angle, right? So, for example, if you convert, let's say in a sentence, you convert all the words in a sentence to word embeddings, okay, then it's not clear if you permute the words, like a regular simple vanilla architecture is gonna honor the temporal information about these words, okay, temporal relationship between these words. Here is an example with a movie. So of course, the movie, the frames have a temporal relationship. It's not like the next frame is going to be completely unrelated to the previous frame. Like a next second is not completely unrelated to the first second, right? Most of the time. So such information is what you want to capture. Um, and one way to capture such information is through RNNs. There are actually many other ways to capture temporal information. In fact, we have looked at least in the in 575, we've looked at time series models a little bit. And in general, outside of this class, also you must have heard of time series models. They all capture temporal information, okay, but they are not models which can deal with this type of data that we are kind of focusing in this course, which is unstructured data, right? So what is the so I'll describe RNN through um, through this diagram. So without going to the details of the blocks. So let's start with the base element. So let A represent a network, okay, some network. We'll get into the details of the network, and it'll have two inputs and two outputs. Okay, so it is like a two input two output box. We'll get into the details of the box soon, and there's going to be a loop from one of its outputs to one of its inputs. Okay, just and so we'll not name that particular loop now, but of course, then the other two input, other remaining input and the remaining output, just call it input and output. So that's this HT and XT. So XT input is fine, and HT is the intermediate output. Okay, so this is a diagram. Is just a compact form for the actual network, which looks like this. Okay, so why did we draw this instead of that? Is to show that the A block, the black box, will get into details soon, has the same parameters. Okay, although I've written several boxes here, they all have the same parameters. Let's say there's a matrix, let's say 3x3 matrix, with a few numbers, which are, let's say, the weights of this network or whatever the function here is the same 3x3 numbers everywhere. Okay, so that's why you can kind of, so this is called the unrolled diagram of a network like this. Okay, and this is called a recurrent network because there is a repetition here, and uh, and and so you can ask what's happening at this input here, because this only seems like three edges, and what's happening here. You can discard this. You can give some dummy input there. So all the A blocks have two inputs, two outputs. The output of the previous A block is connected to the input of the next A block, but they are the same A block. Okay, it's just like calling the same function again and again and again. Okay. Um, Yeah. So this sequence is kind of useful for working with. So this, I guess, unrolled diagram or this type of network is useful for working with sequences. So you can have sequences of images here, or sequences of words here, okay, or or you may not even have sequences. You may just have one input here and no inputs later on. Okay, um, but you can work with these things. Um, yeah. So here I'm just saying that, so this, let's call this a stage. And as I said, all of the A blocks have the same parameters. Okay, it's like the common filter type of an idea, but it's, that's the idea here. And this one, one this square bracket or the bracketed area, I'm just calling it a stage. Okay. So note that there is no time component here. It's really not a, although I'm talking about persistence and so on, it's literally just some computation. So if I give all these inputs, the inputs are getting computed in a very messy way here, and then some outputs are generating. Okay, it's all instantaneous. There is no. I mean, it could be that your, let's say this is a sentence. Yeah, I need to have the full sentence here. I mean, I can, if I want to feed one word at a time, I can do that, but I need these numbers to actually compute those things. Okay, so all I'm saying is it's just unrolled one sentence as the input and some hedges as the output. Now I'm calling them hedges and not Y's for a particular reason, um, and we'll get there. But for now, let's actually uh, delve a little bit deeper into this A. So you can think of this hedges as like outputs. Okay, some maybe this is like a class level prediction also. But I'm using hedge because they will be called hidden layer outputs. Okay, hidden state. There are different names for that. So now we'll look at some notation that kind of will be useful, and actually the most useful one is uh, I guess these two operations. I mean, edges, arrows we knew were actually just going from one computation unit to another computation unit, or one computation node to another one. So for us, NN layer will be this yellow type of box. Okay, and why do I need this notation is because we'll look at the internals of an LSTM, and we'll kind of use these kind of repeatedly over the next 20-30 minutes. So kind of just remember this. Two interesting operations are concatenation and copy. So what is concatenation and copy? Concatenation is just two vectors. If I have a vector of length 5, I mean dimension 5, a vector of dimension 3, just concatenate them. Okay, v stack or head stack, whichever direction you want. And copy is just the same vector being fed to two different inputs. Okay, we have seen this before. So here's a vanilla RNN. Okay, this is the simplest RNN that you could write it by yourself in using nn.modules extension. Right, you can put a for loop and just do this like some number of times. Let's say in this case 3 number of times. So what is the inside? So the A block is exposed here. It's basically doing the following. So it's taking some input, okay, some dimension, let's say 5-dimensional vector, and it's taking a second input. Remember, there are two inputs, two outputs. It's taking a second input from the previous A computation. Okay, that could be some dimension. Maybe it's 3 dimension. Okay, so 5 dimension, 3 dimension, concatenate. So some 8-dimensional input. Okay, so this is a neural network layer. Okay, this is a neural network layer, which just means it's a linear transformation, W times input plus B. Okay, that's essentially what's happening. And then here I've written tan H. You can think of ReLU, tan H, sigmoid, all of these are just some non-linearities. Okay, and then you produce output. Okay, let's say the output is 3-dimensional, so that it can go to the next A. Okay, so that everything is consistent. I said this was 3-dimensional, so let's make this 3-dimensional. And the split just means the 3-dimensional thing is also the output. Okay, maybe I'm doing 3-class classification here. Okay, at that level. So is the vanilla RNN somewhat clear what's happening at a computation block?
Explain the calculation, like when you are combining xt and
Yeah.
xt minus 1. So
Yeah, this one.
is,
Yeah.
you said one is 5 dimension, one is 3 dimension.
Yeah.
So you are just putting them back to back, or you are
Yeah.
doing some
Concatenation. No addition or anything. Here is just concatenation. Yeah.
So your final vector would be like 8 dimensions.
8 dimensions. Yes. I just gave you a simple example. It doesn't. I'm just saying that the hidden. So this is called, as I said, it's a whatever hidden state that can have a different dimension than input. That's all. So in this case, it was like 3, and what you said is fine.
So when you said for every block your weight vectors is same.
Yeah. So the weight vectors inside. So in this green block, no other computation is happening. This is itself. This is the only computation. Some concatenation, some copy, and one nonlinear transformation of a block. So what exactly is happening in there? It's basically, I think I have the. Oh, I don't have it. I have a code there, but it's basically some W times x comma h t minus 1. So this is 8 cross 1 plus b. So this times tan h. Okay. So what is W? W's number of columns has to be 8, right? And I'm just saying that the number of rows, let's say, is 3 cross 8. so that it produces something which is three-dimensional, and then again the three-dimensional thing goes to the next part of the for loop and is also output in this case. I'm just, instead of two outputs, I'm just saying the two outputs are the same three-dimensional vector. Okay. So first you zoom out. Okay, ignore the whole thing inside. There are two outputs, two inputs, right? Here there is no input, but just think of there's some dummy input, zero zeros, all zeros. So that it just turns out that in this implementation, the two outputs are pretty much the same. Okay, it's just a copy of each other. So it's really one output, and two inputs are just concatenation from the previous value and the new information. Okay, input. That's inside the box.
If you want to concatenate on the third block, would you build it on top of what you've already concatenated, or do you only take the input of XC?
No, remember this is like three-dimensional. So this is three-dimensional. So this is 3D. This is three-dimensional. This is eight-dimensional. And this will also be, let's say, eight-dimensional. We know that this is three-dimensional again. So it's the same operation. It's the same W being applied again. So this plus this, not plus, but like concatenated, it's the same thing. Actually, let's look at the code, kind of keep it everything very well grounded, at least for now. So in NumPy, okay, so here's, I'm not using here NumPy, sorry, what is it called, PyTorch, but you can see here's a RNN, okay. So basically you initialize, so H, is all zeros at the beginning with some len of H, and len of X is like the dimensions. So in this case it was 3 and 8, and so I'm just saying initially you set the W's to be some random values, which is that plus, so that is the output. Now it's 3 and this is 8, 3 plus 4, and then bias is whatever len of H, like 3 dimensions. So that's the initialization of the RNN. These are the only parameters, W and bias. Okay, H is not a parameter, but H is just some initial dummy value that I have to start with. Okay, because there's one input that I need to provide. And then the stepping is like every time I get an input, I just need to do W times xt comma h, the stacked version plus bias, and then the h is output. H is stored as a field in this class, and then you return the same thing. Okay, the copy. Okay, output the same. And np.tanH of this activation that I computed. Okay, wx plus w times whatever I wrote before, and then so this is just one step. So if I want to run that RNN in a few loops, let's say 5 times, and you just keep RNN not step, keep calling it 5 times. Okay, that's it. Is the API clear? Like what's happening at the high level from what we saw in the previous diagram? So maybe there's a lot of text here, but to kind of see it offline, that this is like a pretty much a self-contained RNN code. Okay, but you'll not do this, but yeah. Okay, so let's actually start with a simple example. Language model. This is not really a word-level language model, but a character-level language model. It just means that my words are actually just characters, so we're not really thinking about words. So how do you build such a language model using this type of technology, this type of technique? You start with like a large text database, and then so what does the language model do? We just want to build the probability of the next character given the sequence of previous characters. That's what we want to do. So x0 to let's say x5 are going to be some 5 characters, and I want to say what is the next character, okay, given these characters. So as I said, we can generate new text, and we can also use it for classification tasks to improve classification. So let's see. Here's a very so here's an idea, just idea. So let's say our vocabulary has only 4 letters: H, E, and L, and O, and our training sequence is H, E, L, and O. Okay, so we have 4 training examples. Okay, these are 4 different observations you can think of. Okay, they are all related to each other, of course. So first training, for the first training example, give H is the input, and we want to predict E. Okay, first example is just that because it's very short, right? We are only looking at 1 character input, 1 character output. Second example, we have 2 character input and 1 character output. Third example, we have 3 characters input and 1 character output. So it's 3 different examples of 3 different lengths. Okay, that's also important. So I need to run the for loop for different lengths in this example, and you'll see that you don't have to do it separately actually. And So that's the training sequence, 4 examples, and you also want to encode each character as a. In this example, I'm just taking 4, but you can encode it as like a 10-dimensional example if you want. But each character is just like what to vec, right? I want to do character to vec. Okay, I just chose it with 4 because there are only four characters in this vocabulary, so I can at the very least I can do a one-hot encoding. Okay, literally the first coordinate being 1 means H, and second coordinate being 1 means E, and so on. Right? Is that clear? Okay. So here's the example with when I gave all the four characters. The last example, last observation pair where HELL was given, and I need to produce O. Okay, and when I gave HELL, I need to produce O. When I only gave HEL, I need to produce L. Okay, when I give HE, I need to produce L again, and when I give H, I produce E. Okay, you can see that there is no issue here in the sense of like I can think of 4 different examples, or I can think of the final example and one shifted output. Okay, so it's basically the first 4 letters of hello as the input, and the next the last 4 letters of hello as the output. Okay? Because in this language model I need to just predict the next character. So instead of 4 different examples, I could just create one, or I could do 4 different versions. Okay, so it's all the same, and so what's happening? So I start with an input layer, one-hot encoding in it. In this case, uh, H is 1 here, and E is some 1 here, and so on. So I got the x0, x1, x2, x3. Right? These are 4-dimensional vectors, and then I just chose the tarnished layer in between, so that I can have a hidden layer which is of size 3. Okay, so the little hidden state I'm saying is 3 dimensions. So the W matrix here is going to be 3 cross 7. Okay, where 3-dimensional hidden vector, 4-dimensional input vector that needs to be transformed into a 3-dimensional vector. Okay, and you can see that there's also a transformation here. I'm not just passing the H itself as the output, but this 3-dimensional vector is again getting expanded to a 4-dimensional vector. Okay. So that is just linear transformation. Any vector you can change it to another vector by having another weight matrix here. Okay, right? So think of that as the softmax layer. It's not really the softmax operation yet, but think of that as this W2x, W2h plus b. Okay. Any questions about what's? I mean, this is just an example with some figurative numbers. So what we want to do is that we want to, when h is in, we want to set up the weights of this blue edge and the weights of the tarnished layer and the output layer such that when h is input, then e, which is the second coordinate, is as high as possible. The ones highlighted are the true classes in this case, right? We just want those classes to be high as possible. And how do I do that? There's going to be cross entropy loss for this guy, this pair, cross entropy loss for this versus this pair, right? Remember the 4 examples: cross entropy loss for this and these 3 pairs, cross entropy loss for this and these 4 pairs, right? So 4 cross entropy loss terms. Okay, you can think of 1 example and 4 cross entropy loss terms, or 4 examples and 1 for example, and that's what you want to make. You can take a gradient with respect to that, change the parameters such that cross entropy loss is as low as possible. Any questions? So it's the same as before. So these are scores. Think of these as scores. You do an e to the power 1 divided by e to the power these 3. You get some number for the first guy. So those are the p hats. And the cross entropy would be for this, because the true label is e. So the y will be only picking the second probability. Okay. So that number. So the negative of that number is what you want to minimize, okay? Or you want to increase the probability, log probability. Do you want me to write the math equation? Okay. Okay.
So you started with the hidden layer having all the same parameters
Uh,
before you start running your model, and after we start training it, and then each of the nodes in the hidden layer are going to have eventually different.
So it's basically doing this, except I'm not doing the final. Uh, yeah. So these are the two parameters in the RNN RNN block, okay, which is the so wx plus b. So w times so this self.h is a three-dimensional thing that I showed you in the center of that diagram. Now I'm just saying that there's a part is missing in this code, which is that h is being transformed by softmax operation. Again, some w2, w2 times h plus b2 is happening, and then I do a those are the scores, and then I do a softmax operation on them. Okay, that's additional thing which is not shown in this code, but these w's are being changed to ensure that the output labels are the inputs are predicting the output label.
And these, so on the next chart,
Yeah.
Your hidden layers already have weights in them. So this is.
These are not the weights. These are some example hidden layer outputs. So this is like, think of this 0.3 minus 1 0.9 as some matrix times inputs are like 0 0 0 for the initial hidden layer. There's no input, and let's say 1 0 0 0.
Because you're gonna have 7 weights. That's the output at 0.3. That's.
Yeah. So this is a 7-dimensional thing, W, and then also plus B here, which is 3-dimensional, 3 cross 1, and this is 3 cross 7. Yeah. So initially, like given all zeros and this, the W numbers are such that I got these 3 numbers. Similarly, with this guy and these two now, with the same W, I got these numbers, and so on. Just an example.
You said that I think for every step it'll be the same weight matrix. There's not a different weight matrix.
Yeah. So all these numbers, like this number has been computed from the same W. This number, this vector has been computed from the same W. The only thing changing was the input. Yeah. And so when you backdrop, you just have to update the one single W matrix, okay, as well as the bias vector.
So as it back propagates, all those vectors will change together.
W will change. Yeah. W will change and B will change. That's what we'll do by.
But it will be the same for each node.
Yeah, it's always the same W. Yeah. Yeah. As you backpropagate, so think of it as a computation graph, okay, where the computations are happening. So remember, this cross entropy has influence from this guy, this guy, this guy, this guy, right? There are 4 places that W was used to get that loss. Now, if you take the loss with respect to W, then the 4 places where you will have gradients, you kind of accumulate those gradients together. Okay. Remember, there was this. If the same W participates in multiple paths and gets to a loss value, then you have to kind of add gradients. There was this in the first lecture. There was an example slide like that. So you have to add those gradients and then update the W. So let's say W is 3 cross 7. The gradient of loss, this loss with respect to W will be whatever is a 3 cross 7 dimensional matrix, and then you do the usual SGD style or whatever you use. Okay, there are many different optimization techniques. Yeah, I mean that's yeah. Here I just say what I just said. So any questions? I mean, I think we had several questions. So let's move to LSTMs. Okay, so what is LSTM? It's basically just an improvement of that block. Initially, we started with the vanilla RNN where the block was just a tan h of a linear transformation. Okay, Wx plus B. So we want to change that inside to kind of really capture the long-term information. And in fact, the previous RNN would also try to capture the long-term information because there is information being transferred, information about what happened here is being transferred all the way here, right? All this information, remember. So at this point, whatever the H is, it's an outcome of all these previous H's and previous inputs. So hopefully it does capture something. The W matrix is such that it captures something about the previous inputs while predicting the next output. Right? For example, for this, for HEL, you're supposed to predict L, but for HELL, you're supposed to predict O. So the previous letter is not, previous letter is not just enough, but the previous information is kind of needed to predict the next character, right? That's non-triviality. So L can predict sometimes L, it can predict sometimes O, it can sometimes predict white space, whatever it is, right? So the information that appeared way before, like HEL or maybe space here or something else, they all matter in the next character prediction. Okay, that's the long-term aspect that we are trying to capture. I mean, you can do the same thing using Markov models. Remember what we did in the previous lecture? So this is a benchmark. I think you probably have to do Markov modeling in the assignment as well, maybe. Anyway, so LSTMs. So we were looking at, as just recall, we were looking at RNNs because we wanted to enable the network to kind of see the past information. But the question is, can they persist all sorts of information? Can they? So as the name implies, can they persist both long and short information? The vanilla ones. Well, it's not clear. Yeah, so let's say consider model predicting next word given previous words. Let's say if there is some text saying advanced prediction, and the next word, let's say, is suggested to be models, right? Here the immediate preceding words are useful, but when like in this sentence, like I went to UIC and then eventually you say I lived in something, can the model kind of spit out Chicago as the most likely word? It depends context, right? So maybe in between nothing about nothing about the location was kind of said, but because you went to UIC somewhere ahead, further ahead in that sentence, that should kind of guide the model to say Chicago. So if the model can somehow remember that hidden vector, hidden state, can somehow kind of still remember some information about this, maybe it can predict Chicago. And how will the hidden vector remember? It's only through the weights, okay? Because I just have to tune the weights for this corpus such that if there is UIC, then the likelihood of saying Chicago after lived in is high, okay? So that's long-term information, and this is what I mean in pictures, like previous information. So this is immediate previous information, but this is like information after these 3 dots represent a lot of time, and then some hidden node that needs that information. So it's kind of hard to do the second part using vanilla RNNs, and so there are some ways to circumvent it, which is what I meant here. Vanilla RNNs are unable to learn or connect long-term information when they kind of update this W matrix, and so there are some fixes and some new architectures I've tried. These are empirical. There's some reasoning that we'll go through in the next few minutes, but somehow these tend to do better. Okay, and these are actually standardized. So in Torch, you can just nn.lstm or nn.gru will essentially implement what we're going to discuss next, but we'll go into the internals of what it is. Okay, so here's the diagram. Okay, it may look a little bit complicated, but it's good to understand this only not so that we can really understand what an LSTM is, but you'll see that new architectures have been proposed in the past few years. They all will have like similar type of lot of transformations happening. If you're comfortable with this case study, then you should be like comfortable with what other transformations are happening in other architectures. Okay, so is the goal clear? The goal here is not so much to understand the nitty-gritties of LSTM itself. We'll go through this case study, but it's also useful to do when you look at other architectures in the papers. Okay, and in fact, in the syllabus page, I have 2 papers listed. So one of the papers is actually quite a breakthrough. It's called "Attention is All You Need," and that's related to transformer networks. We'll get there today, a little bit later. So you should maybe try to read that paper offline. Okay, and the second paper is something related to some model called BERT. Okay, BERT is just an improvement over that attention is all you need paper, but it's kind of the it's really kind of transformed the natural language processing space over the past year and a half. So certainly worth a look. Okay, in the sense like they are really pushing the performance of any NLP task compared to even 2 years ago, 3 years ago. Like they have huge changes. Okay, so decently like not insignificant changes, I would say. Anyway, so coming back, LSTM is very similar to vanilla RNNs. So in terms of hatches, inputs, it's the same, but there's going to be a distinction between the things which are being transferred from one block to the other. Now there are going to be two outputs, so two things which are connected to the next block rather than a single HT that was getting copied. Okay, so there's going to be some difference. So in fact, there's not going to be copy inside. As you can see, there's some messy or more complicated stuff going on, but we'll kind of understand it. Okay. So the same, there's an input, there's always a HT that can be output, but there's also two like vectors that are being transferred to the next computation unit. Okay, and remember the key idea is still the same. The computation unit may have some parameters. In particular, these yellow blocks, remember, are neural network layers, so they'll have weights. The key idea is that these weights are the same over here, over here, over here, and maybe elsewhere as well. So it's the same weights. Okay, so there is no time component. There's no time component here. It's like a computation graph where things are being reused, just like filters. So as I said, and one additional, I guess, notation, a pink circle represents pointwise operation. Okay, so we'll see, like if you do like e to the power 1 2 and 3, let's say 1 2 3 is a vector and you do ext operation on it, the pointwise operation would be e to the power 1 is going to be e to the power 1, e to the power 2, e to the power 3. So that's what I mean by pointwise operation. Okay, element-wise operation, sorry. So let's understand parts of the LSTM. First is the notion of cell state. Okay, so we're just discussing. So we'll kind of understand. So remember we need to pass information from previous cells or previous previous blocks or stages where some XT was passed and some HT was created, right? Maybe that XT there was like those words, like UIC. Now some information has to be passed forward, right? So that information you actually pass through this CT or the cell state vector. Okay, I mean passing just means that computation. The vector maintains some numbers which tend to have information about previous inputs. Okay, previous inputs and previous things that have happened. Okay, and the vector horizontal line just means so there's this vector from this to the beginning to the end of this block is getting transformed in a couple of locations. Okay, there's some element-wise multiplication happening, some element-wise addition happening. Okay, so think of this. This is a vector. It's happening. It's undergoing two changes, and then it's being forwarded to the next cell. Okay, next stage. Okay, and as I said, okay, this I think I've already explained. There's an input, there's an output, and there is two things being passed separately from one stage to the other. Okay. Now, cell state, it basically is kind of the intuition for the cell state is that there is some information flowing along this vector. So in the sense that at the beginning there's a CT minus 1 vector. When it passes through and is being passed to the next stage, the information in that vector, the numbers in that vector, they can be changed. Okay, and they're being changed by this element-wise multiplication and this addition operations. Okay, so let's see how it happens. So we'll start with so even before understanding how the cell state is being changed, we'll understand the notion of gates. Okay, and gates are also things that appear in many other architectures, so good to understand it. So what is a gate? Gate is nothing but a gadget or a computational block which optionally lets information through, in the sense that in the sense of this example, let's say there's a vector, okay, and I want to change that vector. Okay, so think of this as the input, this is the output. Okay, but I want to change the vector. Okay, how do I change the vector? Let's say there are a few numbers in that vector. Let's call it 5, 4, and 10. Okay, let's say I want to kind of somehow go from here to another vector where maybe I want to kind of kill this number 10. I want to make this 0. Okay, how do I do that? I kind of do an element-wise multiplication. with numbers which are between 0 and 1s. Okay, so that's achieved by this transformation. But what's happening is 5 can get multiplied with 1 itself, 4 can get multiplied with 1 itself, and 10 can get multiplied with a number which is very close to 0. Okay, and if I do that, then the output is 5, 4, and 0. Right. So that's the way I can optionally let information as an information. Think of each coordinate of this vector as carrying some information, and I'm kind of attenuating that information in each coordinate. Okay, and that's being achieved by this element-wise multiplication. And the input to do so before to do that multiplication is u. Okay, then why is there a sigmoid transformation happening here? Is because u itself may not be a number between 0 and 1. Okay, so we are generalizing by saying, okay, whatever u is, first let's transform it, linear transform it, and then apply sigmoid rather than maybe directly apply sigmoid on u, and then do an element-wise multiplication. That's the notion of a gate. So what is the gate doing? Is flowing. Think of it as water, right? So think of 5 units of water, 4 units of water, 10 units of water flowing, and then gate is like shutting down the water flowing in the last one. Okay, example.
The sigmoid function applied to WU plus B.
Yeah.
You've got a single scalar value, and that's going to be multiplied to each value in the vector.
Yes. So good question. So sigmoid of let's say vector 1, 2, and 3. Okay, is just 1 by 1 plus e to the power minus 1, 1 by 1 plus e to the power minus 2, 1 by 1 plus e to the power minus 3. That's the sigmoid operation. Yeah, it just normalizes the numbers to be between 0 and 1.
Okay, I thought the x was going to be considered a pointwise operation that we were talking about earlier.
X, where is X?
In the
Yeah, once you do the sigmoid, you get another vector. This is the vector.
Okay.
Right? That vector is getting multiplied by v element wise.
So based by like index.
Yeah. So think of this last number like minus 10, minus 20, and 3. Okay. So then this is plus 10, plus 20. Oh, sorry, I should have done the opposite. So in this example, I'm just making these to 0 and I'm keeping 10 as 10. Okay. Because you can see that 1 by 1 plus e to the minus 3 is almost 1. So 10 remains 10. These numbers are huge. So this is like essentially zeros. And element-wise multiplication 5 and 4 with zeros is 0.
So, like, there is not something. So if you have to like initialize the u vector, we
Yeah.
cannot do it randomly, right? Because
Yeah.
we're trying to control some features of the v vector.
Yeah. So if you turn out, it's a teaser, u vector is going to be some transformation of the current input and there's the ht minus 1, which kind of we have ignored so far. It's going to be some function of that. So gate is being controlled by current input and some information from previous cell. So we're not explicitly, so no control is happening. These are blocks. Inside the blocks, we're understanding what's going on, and the weights are, while training, while minimizing cross entropy loss, all these weights are tuned such that such controls happen. Okay? That's the interpretation, post hoc interpretation of what's going on here. Maybe even while designing, that was intuition. I don't know. Okay. So the LSTM has actually 3 gates to control the cell state. So one is the gate which we already saw. So let's look at each of the gates actually. So we saw So let me talk about the first gate. So I think I should probably show you the. We'll be talking about this part, okay, first, and then we'll get to the other 2 gates. So this part is called the forget gate. Okay, forget gate. It's basically because I'm multiplying it with sigmoid, and sigmoid can only at most be 1. If they all are 1, I'll just forward the same numbers before. But they're close to 0, then I'm really forgetting what the numbers were there on those coordinates, right? So yeah, that's what this explanation means. So, and in fact, the forget gate is over here. As we just discussed, the ht minus 1 and xt are concatenated, okay, and then a sigmoid transformation. So wx plus, so w, I've written it here, w times ht minus 1 and xt concatenated with each other, and sigmoid. So that's the gate u or ft that I'm calling it, and then that gets multiplied to the element-wise multiplication with the cell state kind of makes you forget. Okay. For example, things like here is an example. This is just post hoc, just a running example. So cell state may include gender of the current subject, and maybe that was useful. But when a new subject is observed, then you want to drop that gender. Okay, maybe you want to retain some other gender. Okay, it's just intuition. Okay, it's not all these are numbers, but hopefully they can capture such information so that they can do the right translation or whatever the task is. Okay, because they have to capture gender information if they're going to translate from when there's change of one subject to the other. Okay, so next part is deciding what information we'll store, what new information we'll store. Okay, what new information. So we already like multiplied element wise. We forgot some coordinates. Now we'll add something. Okay, and to add that we'll need the input gate and the tanh gate. Okay, and what does input gate do? It just decides what values to update. Okay, and let's look at how actually. So input gate decides what values to update, and Tannish layer actually creates the values that need to be added to the cell state. Okay, so think of like to add new information, I need to decide what is the new information and where to add it. Okay, so where to add it, is decided by the input gate, and the new information itself is is decided by the Tannish layer. Okay. So that's this part. So we just dealt with this forgetting part. Now we are thinking about what is new information that's getting added. And remember, everything is determined by the same thing in the sense of previous ht-1 and xt. Okay? These are the two things which got concatenated, driving what to forget, driving what to add. Okay? And for that adding, I said we need two things. One is where to add and what to add. Okay? So Tannis is creating just what to add, c tilde t. Sigma of this input is deciding what to where to add. So the new information, element-wise multiplication with this tells you okay where to add, and then you if you do if you control this gate, then that information is getting added to the cell state vector. Okay, so that's not highlighted here, but yeah. Like for example, add the gender of a new subject to the cell state. This replaces the old value we are forgetting. This could replace the old value we are forgetting. Okay. Okay. So that was these two parts. At this, once we do these two parts, we have already got into the CT, which we can pass to the next cell. But we have to do two other things. One is we have to produce this output, and we have to give the same output. It turns out that in LSTM we give the same output in the next cell as well. Remember, we're producing two outputs to the next cell. And what we're going to do is, because we have a cell state, ST is just going to be some transformation of the cell state. Okay. What do I mean? I'm just saying that we have a cell state. Some transformation of the cell state is going to be output, and the same thing is going to be passed forward as well. Okay. So that's the next step that we're going to focus on. So sorry, when I said last step, I was saying that once you create what to forget, you do that. What to add, you do that, and that's what I said. The modifying the cell state. That's this. Okay. And once you do that, then we focus on the output. And output, as I said, is just going to be a transform version of the cell state. Okay, cell state is a core thing, and then some arbitrary transformation of that is going to be the thing which will output. And for that also we have two things. One is we'll transform the cell state through a Tannish layer. That's just a nonlinearity, because there's not too many nonlinearities happening. It's not like a deep network with like lots of layers and so on. It's just the same Tannish or sigmoid layers. In fact, Tannish is the kind of core layer here. And then once we do that nonlinear operation, we can scale it with the sigmoid again to kind of capture what parts of the cell state we want to output and what part of cell state are not going to be out part of the output. Okay, as in this is another gate is what I meant. This is the third gate. Okay, so in pictures again, same input ht-1 and xt drive the gate, and cell state is getting transformed here. Note that this is actually not a neural network layer. It's just a vector element-wise multiplication of the vector. Okay? There's no neural network layer here. It's just a cell state transformation. And then the gate is controlling what Again, if it's 0, then it's setting that number to be 0. If it's 1, it's like passing that number through, and that's the number which is being HT or HT. Okay, it's the same. It's a copy here. So that's basically the operation. So for example, if we saw a new subject, it may output information related to the actions. For example, whether the subject is singular or plural, so verb can be modified appropriately. Right. So those are things that can be HT. Okay, like So that's it. So if you just a summary, we looked at the core notion of the self state that needs to be modified. So first we forget what information we want to forget. I mean, this is literally is just a control on what information you want to forget, and this is the new information that you want to add. Okay, with the gate and in transformation, and then we actually do that forgetting and adding, and then the self state is modified and passed as output and to the next step. Okay. Yes.
So I have a general question.
Great question. Yes, tell me.
So when the guys were coming up with this algorithm,
Yeah.
they realized that the prior algorithm wasn't taking into account this wasn't able to deal with old information.
Yeah.
Right.
Yeah.
And so when they came up with, for example, the forget gate,
Yeah.
how that works.
Yeah.
They started from that idea, right?
Yeah.
And presumably just got a whiteboard and started saying, if we connect in this way, it's
Yeah.
going to decrease the value of the old information.
Yes,
right?
yes.
And tried various formulas, and then do they empirically test it to see which one works best?
Yeah. So what we are not looking at the historical evolution of these test networks. Right? This is the one which works best. That's why we're studying it directly.
Right. I'm just curious how they.
Yeah, there were many variations since this is about now 30 years old. Okay. 30. Yeah, 1988 maybe. I don't know. So these are there are many variations. I mean, this is just one example, one variant that we are studying, and it's just so some of it is intuition driven, coupled with empirical evidence that these do capture long term dependencies and are able to solve those sequence problems better than the previous state of the arts. Yeah. Yeah.
What kind of problems can LSTM solve? We talked about translation.
Oh, sequence. Yeah, mostly translation, image captioning. I mean, that's what in the context of this, I guess, course. Those, time series methods. Any place where you would use a ARMA model, you can use an RNN.
Okay. So question answering would not be, or query detection would not be.
Question answering would be. You can use this. Yeah. I mean, question answer. You have to create a certain answer sequence, right? So basically, you can use this for language models, and language models are kind of the key component whenever you want to create sequences and sentences. I mean, if your task involves a particular well-structured input and output, like a sentence, then you would need language models, and they would be generated using such trained networks. Once they have trained using a large corpus, they'll be good language models. I mean, not just these, but now, as I said, there are newer networks which are slightly better, which I'll discuss next, actually. So just as a aside, there's one more variation here. Variation as in sense. So examples of RNN, right? So remember, we saw vanilla RNN, we saw LSTM, right? And there's one more variation which has yet another different wiring about forgetting, adding, and so on, which is called gated recurrent unit. And this is also a different design, and you have both these designs in your nn dot module. Module, the PyTorch module, and it has a bunch of equations. Let's not worry about it. I'm just saying that both seem to have some reasoning. I'm not going to talk about the reasoning for this different cell, but both seem to be empirically quite good in terms of modeling temporal. In temporal tasks, the task which involves sequence information. Okay. Here's another variation. So now we'll kind of zoom out. Okay, so now let's not worry about the internal details of the A block, whether it's vanilla or LSTM or it's GRU. Now we can do some other things. Okay, and you will see that people play with these ideas as well at one layer higher abstraction, which is this, right? So instead of HS here, okay, you can connect. You can kind of double up the computation graph. just think of this as a huge computation graph, right? Given this input, you are basically like transforming all the way to these outputs. Okay, so these x's are not the same as these x's, but they're actually some x. This sequence got transformed to some other sequence that further got transformed to finally these h outputs. Okay, just think of it as like a layering of computation graph. That's what's happening here, and you can have more. You can deep. You can increase the depth. You can also yeah, I mean, I guess that was, I think I don't want to show more examples of with that. So that was that. And yeah, and for us, we are not going to really cover with the new RNN architecture. We're going to just use the GRU or LSTM kind of we saw. And as a practitioner, that's pretty much what we'll do because they have been evaluated. I think this paper here, this 1503 04069, kind of evaluates lots of different LSTM architectures and figures out like which ones are actually the best performing across a bunch of tasks. I think so. That's kind of good enough for us. Given that reference, we can just pick the best performing ones. Okay. Yeah.
What would be if you were like examining a video with that? What would be types of output that you might get?
Are you working with video data? You mean?
Yeah.
So x0, x1, x2 could be frames of the video, and you need to have tagged video, right? So maybe there's already a tag of like at this frame corresponds to maybe even each frame of the video may be segmented or may already have like tags or labels. Sorry. So if you already have training data like that, then you can use sequence to sequence methods.
But the point is to like identify objects in the video, or to you could output a
Yeah.
description of what's happened in the course of the video.
Yeah.
Also?
Yeah. If you have such paired data, you need to have the training data. You need to have the video and the text. So you can have full compression of the video. So think of not immediately looking at the H values, but you pass all the video frames, okay, and get the last, for example, last hidden output, and then use that hidden output as a starting point for like generating text.
Like if you had
We'll-
a narrative that was describing what was going on in the video.
Yeah. We'll see some examples and it'll become clear. Yes. So training, actually not much to say here. Actually, pretty much the network consists of differentiable operators. So those gates were cleverly designed, using sigmoids so that everything is differentiable. Okay, so it's just there's no sudden like non-linearity going on, and so you define appropriate loss depending on whatever it could be sum of cross entropy losses, for example, at different stages. Then that would be the loss, and just run backprop. Okay. I don't want to go through this. I mean, in a sense, it's just showing the dimensions. If input is 2-dimension, HT is 2-dimension, cell state is 2-dimension, then this is the more elaborated picture of the same thing that we saw. Okay. I mean, here it's literally showing the each dimension as a separate line. So let's take a break and resume at 8:10.
So,
Yes.
if I want to connect to